Welcome, good morning. This is now the fourth, and we're talking about the atom today. But just a few housekeeping things. One is it is a trial because next week we're dealing with relativity and Bernowski. You may remember that series, The Ascent of Man, did such a good job, literally on site in Bern, Switzerland, with the tram and the clock, that it's well worth seeing. So we've tried that out here a couple of days ago, and but we're going to try out something else today, looking at Niels Bohr's home, and so just to see whether it works. Then the other thing I just mentioned, that there are some essays that have been dumped on the website. The one, Science by Quiet Conversation, that's really about Niels Bohr. And if I had to pick a favorite, and many of these scientists have become very familiar to me and almost associates, and I admire them, but I guess I would put Niels Bohr at the top, and maybe you'll see why at the end of today. So that Science by Quiet Conversation, there's one about Heisenberg and the uncertainty principle. We'll talk a little bit about that today, but that's been more fully explored in the essay. And then there's one, Schrodinger was a very interesting fellow. He ended up retiring to Ireland and became very involved in the arts. And one particular essay was on the scientist as a humanist. So that's worthwhile. Then there's one on the arts and sciences, finding common ground, and one on physics and beauty. So so they're, you don't have to read them all or any of them, but you might be interested in exploring them. So I'll tell you, I think the Nobel Committee found out what we were doing here, because I couldn't be happier with Nobel Prize awards so far. And on your screen now, it should be the one given for black holes. And I mean, we're going to be talking about that next week. It was part of the science series. It was part of the Nobel series a couple of years ago when we were talking about gravitational waves. It's a great one, so I couldn't have been happier. And then some of you who are familiar with the science series will realize that, at least with the Nobel series, is that I've been expecting a Nobel Prize to go to gene editing now for 3 years. And I knew that two major groups were suing one another. There were great legal battles, so I somewhat understood that the Nobel Committee might be a little reticent, but they've come down this year and given it to the people that I think really deserve it. So and we've talked about that in the science series and the Nobel, or not on the Nobel series, but anyway, and in the InfoHealth program. So that's familiar ground, at least it is for me. And it's stuff I've written small essays about, because it, together with artificial intelligence, in a way represent the major threats of science to humanity these days. So, well, let's go on. Handprints on cave walls are universal on all continents. This one happens to be Argentina, somewhere between 13,000 and 9,500 years ago. And it's an interesting phenomenon, isn't it? Because you don't see them erased. Many of these caves were visited many times over several thousand years, and no one seems to erase the handprints or the art. But what is this meaning about putting your hands on the cave wall and blowing pigment at your hand? And so you see these, at least as they're shown here. So what I did here is something I don't know whether you can see this well enough, but I've taken those handprints from that Argentinian cave and superimposed them on a nebula, because really it represents what we're trying to talk about in this whole series. Let's face it, if humans weren't around, or Neanderthals might have been capable, I don't know, they didn't survive long enough, but it's really our species that asks the questions and has been busily exploring the cosmos writ large and tiny, and philosophically and in art and all the other endeavors. And so I thought, well, human hands on the cosmos written large, in this case, an enormous galaxy, is a good way to start. So we're talking about the atom, radioactivity, and missiles. You'll understand why the missiles as we move along. This is, there's so much detail in this. I simply had to choose where to put the emphasis. But in the larger timeline, the Curies, husband and wife, and Becquerel, who was really Henri, who started this whole business of radiation and the study of radiation. And it was Rutherford and his later colleague Chadwick that took advantage of that to explore the atom and found the nucleus of the atom. We'll talk about that. The electron turned out to be a far more formidable part of the atom. Is certainly the spiritual center of that exploration, and people who worked with him, Heisenberg, for example, and Born, and other people could have joined in. So we're going to explore all that. Now, let's just, we've done this before. We've looked at 1900, and we looked at 1930, and what was found in between. Well, as I mentioned, in the year 1900, there are some people, including Max Planck. By the way, did you notice that that first Nobel Award, it was the Max Planck Institute? So it's the same one that we talked about with respect to black body radiation and the quantum a week ago. So that very Max Planck questioned the existence of the atom right up to 1900. However, 3 years before, J.J. Thomson at Cambridge had discovered the electron, so it's pretty hard to hold that it doesn't exist. And moreover, that the atom could be fractionated or broken down into its constituent parts, and first small, the tiniest part, was the electron. So let's just carry on. Now, in 1930, well, no doubt the atom exists. Last week I talked about the evidence for that presented by Einstein when he looked at, when he reimagined that black body radiation, but also looked at the photoelectric effect, and then did that marvelous theoretical study of Brownian motion, where the end result was there was no doubt anymore that the atom existed or molecule. Both Planck, reluctantly, Einstein with a little more enthusiasm, showed that energy was quantal. The atom was divisible. So Thomson had showed the existence of the electron, and Rutherford the proton, and his colleague later in the early 1930s showed the existence of the neutron. So there we are. Now, what we're going to explore today is that the world of the atom, the rule book changes. And we're talking about quantum mechanics here. It becomes, for those familiar with the Newtonian universe, the rules have suddenly changed. And certainly the Heisenberg's uncertainty principle highlighted that one. So let's just carry on. Well, something about the atom, maybe it's not self-evident, but I've said this before, most of us is empty space. Why? Because the size of every single atom. That people have used various analogies, that one is the fist in the cathedral. The fist might be likened to the nucleus, and the cathedral to the whole atom. And so atoms, look at all those decimal places. Atoms are 99 to 10 decimal places percent empty space. Why is that important? Because it shows you that atoms can be compressed, gravitationally compressed. And there's a lot of space to be compressed into. That explains, for example, why neutron stars can be so dense. They're simply filling in all of that empty space in the atom. So a lot of space in atoms, and therefore a lot of space in us. Well, let's look at the Curies initially. Now, interesting, Marie, she initially born in Poland, has a very interesting kind of life story, which I'll say a few things about. But she married Pierre, and the two of them investigated radioactivity at the Paris School of Physics and Chemistry. She won 2 Nobel Prizes. The first one shared with her husband, and she unfortunately didn't live to see one of her daughters and son-in-law win another Nobel Prize in, I think, well, we'll see in a few slides, but I think it's 1935. Anyway, we'll talk about that. But they as a family, and right through to the next generation, studied radiation, and either spontaneously emitted by some ores, uranium. Now let's look at this. Rontgen, the discovery of X-rays. In fact, this was the first Nobel Prize awarded, 1895. And this Henri Becquerel showed that natural materials such as uranium spontaneously generate weak currents, but they also generate, or it also generates X-rays. And hence, I mean, this really captured the imagination because there were photographs of the skeleton, and I don't know whether you remember, but I certainly do remember as a kid, you could walk in and buy shoes and put your feet in this little device, and you could see the bones in your feet. Fortunately, they don't do that anymore. So Marie and her husband, you know, it's amazing. They spent an enormous amount of time in an abandoned shed. That was all they were given. Or isolating tiny amounts of radium and polonium from absolutely massive amounts of pitch blende. And they did it chemically and physically. I mean, the conditions were miserable. The place wasn't heated in the winter, and it certainly wasn't air conditioned in the summer. And it was physically very demanding work. It did lead to this Nobel Prize in 1903. Becquerel got half the award, and the Curies shared a quarter each for their study. Just moving along. Well, I mentioned that Marie had the joy of seeing her daughter Irene and son-in-law do successful research, but not win the Nobel Prize. So that's unfortunate. I think, you know, it's not stated explicitly, but Rutherford's research at the Cavendish in Cambridge used radium as the primary source of radiation and therefore particles. Um, and I'm sure he got it from the Curie. And probably 1902 or 3, and there was a dinner party in Paris, and getting around 11 p.m., Marie went inside and brought out some of this radium, and it had this lovely kind of greenish glow. And but you know, both of them, she and her husband, essentially died of radiation poisoning. Well, no, he didn't. He was killed in an accident. Very bright student. He was also a lucky one too. He one of the few times he came second was for an award for a foreign fellowship, and it turned out that the person who won it turned it down. That was Rutherford's step to Cambridge as a fellow. Rutherford was physically an imposing person. He was loud. Notice the sign over to talk softly, so that shows some sense of humor in the laboratory. But he was very direct. He was an excellent experimentalist. He thought very directly and simply and intuitively, and most of his intuitions for experiments turned out to be right. They were the right things to do and paid off. I'm now kind of moving on to Niels Bohr, because I'll come back to the nucleus in just a second. But there's an interesting period, I think in 1908, 9, anyway, where Niels Bohr comes to Cambridge, and he was to be a research student under J.J. Thomson. He was the fellow who discovered the electron. And already Niels Bohr has been thinking about trying to make sense of the electrons in the atom, and were they in orbit, and what determined those orbits? How does that actually work? And so he had this manuscript, and Niels Bohr was very quiet and very deliberate in manner. He was very social, believe it or not. And but anyway, he dropped this manuscript off. For several months, Thomson never looked at it. So finally, Niels Bohr got fed up, and he took off to Manchester to work with where are we here? Hold on, just find out, with Rutherford, and you know, oddly enough, the two men hit it off. Rutherford wasn't somebody to listen. He liked to talk more than listen, and but he and Bohr had this habit of speaking almost in a whisper, very quietly and very deliberately. I mean, he would pause sometimes for half a minute or maybe longer to find just the right word. And so it's all the more extraordinary that Rutherford recognized that Bohr was a really capable person. He knew what he was talking about, and he was very patient with him. So we're going to rejoin and find these stories together here. So I'm going back to Rutherford now. Rutherford, some of you will know that Rutherford uh, spent 8 years at McGill University. It was well funded. It was brand new laboratory facility, and he had good people around him. And actually, in that period of time, he did the work, or most of the work, for which he later won the Nobel Prize. And he also, obviously people overseas, or at least in the UK, recognized his value because he was elected a fellow of the Royal Society in 1903. That's not a small thing. But you know, there was another thing at work here. As productive as he was at McGill, most of the important science, at least in All right. Are we all right? Is that better? Oh, you're muted. Are we all right?
Sorry, everyone. Technical difficulties. Thumbs up if you can hear him better now, if I let him speak.
Oh, can you hear me now?
Okay, okay.
Okay.
Okay, good. We'll continue. Thank you for thanks for your patience, everyone.
Yeah. Well, I'm not sure how far to go back, but I'll try and remember and repeat stuff. Yeah. Rutherford was at Manchester. He demonstrated clear evidence that that the atom was constructed in such a way that it had this very small central nucleus and it was positively charged. But he had no idea how the electrons were arranged. In fact, in the Rutherford model, they were all higgly-piggly orbits, but with no organization to it. That's when the visit of Niels Bohr had such an impact, because Bohr's interest was in the electron. So it was really a meeting of minds, and very pleased and actually read Bohr's manuscript, but more importantly, he listened to him. So, why is this not moving on? Oh, there we are. So now the model of the atom changes, and we know that there's a central nucleus. It occupies a very tiny space in the center of the protons, and much later, neutrons as artillery pieces to actually aim at atoms and break them up and study their structure. So that's the artillery man in physics. And I included this figure because it's Rutherford's figure, and it was really drawn from his days at McGill. And on the right side, the details aren't important. What he's showing is that with each of these radioactive substances, including radium at the top, they break down in stages. And then on the left side, they emit three species of radiation: electrons on the lower right, the negatively charged, the positively charged helium nuclei, and gamma waves that carry no charge. So, and he won the Nobel Prize in 1908 for his investigation into the disintegration of elements. That was the McGill work, and the chemistry of radioactive substances. Chadwick's work, strictly speaking, is outside the window of this series, but he got his Nobel Prize for finding the neutron in 1935. I must say that was an 8-year odyssey for Chadwick. It was so frustrating. There were so many foibles, experiments gone wrong, wrong paths taken before the discovery of the neutron was actually made. And it's an illustration that science is often hard work, and it takes determination and persistence. Now, here are the two men when they would have met. So Niels Bohr and Ernest Rutherford. When we'll talk about the Bohr's model of the atom in just a second, but aware of Bohr's model for the electron and the fact that it worked with the hydrogen, with hydrogen. People acknowledged this as a huge step, and he was rewarded when he went back to Denmark, and he was given his own institute. And this is the institute, but it's an institute unlike most that you're probably familiar with. That whole first floor there was by Niels Bohr and his family. And it created a very social, warm atmosphere in the place. And guests would be and there were guests constantly coming and going. And they would just take up one of the bedrooms, and it greatly facilitated discussions among the theoretical physicists. So, and by the way, that was his design. And this is a lovely portrait of sketch on Rutherford. It's a lovely picture of the man. And later, he was a blackboard man too, illustrating something before a group. Just a few things about Niels Bohr that are really quite extraordinary. Some people have said that Bohr could not think without company. And there is this Robert Oppenheimer at the bottom there, instead of the institute and Bohr's role in it. That it was not the doing of a single man. It involved the collaboration of many scientists from different lands, from first to last. But throughout that river run through it, so to speak, experience for people, it was Bohr who guided and restrained, and that's an important word to underline. Sometimes young people or people fresh into something, they do need restraint as much as encouragement to move ahead. And so we had this. In fact, it's been said, it's hard to know what actually Bohr created, because whatever was created there was a collective creation of so many people working together over years. It was very typical of Bohr he was quite athletic. He liked long walks. He liked climbing. He liked skiing. He liked sailing. And he would always include people, visitors, coming in along these things. And so they would talk for hours and hours and hours, days. When Heisenberg showed up, it was a 3-day hike, and exhausting intellectually for Heisenberg, almost more than the physical side of it. So really an extraordinary leader. When he won the Nobel Prize, he used the money to buy this home, and which you can see there. And again, it's a very informal thing. Do we have that video clip that shows that or not? Yeah. Okay. Well, let's just move on. Let's talk about what Bohr brought to the structure of the atom. You know, strictly speaking, electrons, if they change direction, it was thought, based on classical physics, that they would lose energy. And if they lose energy, they'd eventually fall into the nucleus. So just orbiting around in various orbits around the nucleus, using a Newtonian, from a Newtonian perspective, just wasn't going to work. Now, Niels Bohr knew intuitively they must not only orbit and maintain their orbits, but not lose energy. That's a departure. That's a huge departure from Newtonian physics. And that was just an assumption without evidence. That's just an assumption of Niels Bohr. And they occupied what he called permissible orbits, where they didn't lose energy and they could maintain their orbit. Now, the other great insight, there were two great insights. One is that assumption that at the nuclear, at least at the atomic level, electrons could occupy orbits and kind of spin around like seemingly forever without losing any energy. By the way, in the larger world, or the larger universe, or in our solar system, because my battery's running low. Anyway, in the larger universe, all planets circling the sun and other planetary systems eventually lose their momentum. And at some time in the future, they will fall into the sun. But at the atomic level, they don't. Now, the other thing that was known about all atoms is that they emit light. They emit light and they absorb light. And particular bandwidths of light that they emit and absorb are very specific to the atom. Bohr looked at that and he thought, gee, I wonder if that got something to do with these orbits. And maybe it happens. For example, these orbits, they begin close to the nucleus and then further and further out. And it's been likened somewhat to a stage, or at least that you go into a theater. And the lowest energy seats are those of the front row, or at least the first few rows. But you have to put more energy in it to get to the middle rows, and even more energy to get to the furthest rows out. So if this great insight here was, well, what happens if an electron jumps? And we're talking about jumping. I mean, there's no track from origin to destination. It just was here at one point and reappears at in another orbit, but no track in between. That's another peculiar thing about the quantum atomic world. But those jumps from a higher energy level to a lower energy level are associated with the emission of energy in a particular bandwidth. And for example, in the case of the hydrogen ion, from the third orbit to the second orbit generates red, or light in the red bandwidth. So, and it turned out he was absolutely right. That when and I'm using some of his illustrations here for historical reasons, but there's an example on your right there of the electron moving from the third orbit to the second and emitting red light. And the lower, ignore the stuff at the top, but the hydrogen emission spectrum related to what I've just told you shows you the specific bandwidths for light associated with jumping from the third to the second, or the third to the first, or the second to the first orbit. So linking those two and predicting it, which light, how much energy was being emitted and absorbed, and matching that with the observations that were already known about the spectra of light. Well, that's, he thought he had solved the problem of the atom. Well, he hadn't, because the minute they started to look at more complex atoms, with more electrons in them, that solution didn't work out. So, so then there was a great scramble for several years. And most of this scrambling took place in Copenhagen at the Institute. And it also took place in Germany at a couple of sites. So they learned, several people looking at this learned some more features of these orbits. For example, with Heisenberg, with very complex math, so-called matrix math. I mean, it's very obtuse. They had to reach back a century to actually find it. Came up with mathematics that worked for all atoms, whatever their size. But no one looking at the math could visualize what was actually happening. Louis de Broglie, and then shortly after that, Schrodinger, thought, well, maybe it's related to the wavelength. Remember we talked last week about this duality of particle and wavelength. And it turns out that these orbits can only accommodate whole numbers of wavelengths. So then Schrodinger, and it's a marvelous story, he was on a skiing holiday with a mistress, and his wife was off somewhere else. I don't know where, but and through this several days, came up with an entirely different formulation that also worked. So now we had this curious paradox of two solutions to the same problem, and they both work. How could that possibly be so? And that's where later Dirac and Pauli came in, where they looked at they're really saying the same thing. I know it doesn't look it, but they are saying the same thing. And so that's what occupied quantum mechanics in that 10-year period from, say, 1920 right up to the late 1920s. So, and they also found out some other things about electrons, that they spin. By the way, the fact that electrons spin is a property that we depend on for magnetic resonance imaging, because that magnet, in a way, that magnetic field that's created, you hear that boom, 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 boom going on, that's magnetic field being created in the MRI suite, orienting all of these electrons in a certain order, and then you collapse the field, and they release energy, and that's what's picked up. That's a very simple way of kind of putting it, but the spin, the fact that electrons kind of spin, actually has a practical benefit for us in imaging. So it really worked out. I mean, I think that Niels Bohr maybe put it best for philosophers as well as physicists. And he said that, look, there's a time where there are some things we simply cannot visualize and we cannot know. And our language fails us. There's no proper way to describe it. We use analogies and metaphors from the larger world, but we really can't describe events. And these events are Heisenberg would certainly say this, are statistical events. We can't identify any one single event. But we can say, gee, over time, the probability of an electron being in a certain position is this. But it's only a probability, only a probability. So that's part of quantum mechanics. By the way, that's Schrodinger on the left, and Prince Louis de Broglie, interesting character, I must say, on the right. We don't have time to talk about it. So I want to say something about weirdness in quantum mechanics. Well, first of all, that uncertainty principle. That for example, you can determine the momentum or the direction of a particle, but if you do, you can't tell what its position is. Or if you can determine its position, you can't determine its momentum. And then the one that really unnerved Einstein was this, well, the next two, that the observer changes what's being observed. Just observing it changes what's happening. I mean, it's crazy. Einstein said, so does this mean that if I turn my head around and I can't see the moon, that it doesn't exist? And well, he was kidding, but look at this whole business of entanglement at a distance that you probably heard about, that particles many light years apart behave as if they're in the same dance. They do exactly the same thing. Well, there have been several experiments since to show that actually happens. In fact, some people are looking at it. You may know that China and the United States and maybe some others are developing quantum computers, and they incorporate this entanglement at a distance phenomenon, so that a signal in a satellite and a signal on Earth will be entangled to some extent. So, and the other thing that Einstein really didn't like was the lack of causality. Everything seemed to be chance and statistical, but you couldn't look at it and say, okay, where did this actually begin, and where does it end? So it was the statistical nature of quantum mechanics and some of those other things that troubled them. Well, maybe Heisenberg isn't quite right. Here's in the Nobel series in 2018, you may remember that a Canadian, Donna Strickland, got a Nobel Prize at the University of Waterloo, and for work on developing high intensity ultra short optical pulses. But the point is that this work by these three people, and now it turns out many others, have developed incredibly sensitive and very fine techniques that allow us now to see an atom. And not only see an atom, but we can see the electrons around the atom. Now, not as individual electrons, but as kind of a cloud. And so maybe that uncertainty principle isn't so uncertain as we thought, because I'm sure this will get even better later. Now, I don't know where we're at here. So I do want to say something about this because I've alluded to it earlier. Einstein and Bohr had this really unique relationship. Einstein was very uncomfortable with quantum mechanics, and Bohr, his argument, and I think most people in the field right up to today say, well, it works. It works to many decimal places. It's very predictive. It's very precise. So whether you understand it or not is a whole other matter, but the math works. Well, Einstein had this view that, well, that's just not good enough. At some point in the future, they'll find some underlying process. He liked field theory that will explain Newtonian physics or reconcile Newtonian physics with quantum mechanics. Now, that Nobel Prize that was given this 2 days ago for black holes, that's where Newtonian physics and general relativity, Einstein's general relativity, clash with quantum mechanics. But these two men, they would find excuses to disappear and have these long conversations with one another. And furthermore, Einstein was constantly coming up with these thought experiments to challenge for. Some of them took 4 months to solve, but he solved them all. And I don't know whether I mentioned this, but it's a very moving thing because Einstein died first, and then I think 2 or 3 years later, Bohr died, and one of his colleagues went into the Bohr's private study, and what should be on the blackboard but the last Einstein thought experiment, which he had obviously been working on at some point. So an interesting example of two men who really got along well with one another, but disagreed. And the last thing we're going to talk about this a little bit with the last, there are limits to what we can know. And we've touched on some of them. I mentioned the uncertainty principle. We talked about the atomic universe, which is kind of almost beyond our reach. But there's one that we haven't talked about, and that's are there limits to human cognition? Are there limits to our ability with language or any other tool we have to describe phenomena? Are there limits to our ability to visualize things? I think there are such limits. And I say that for individuals and collectively. The Nobel Prize on black holes, that involved a lot of scientists. The two major groups studying the center of the Milky Way and studying the giant black hole there that is millions of times the mass of our sun. And there are all kinds of haze and other things get in the way, but they've solved problem after problem in a row, just the way scientists do. But the point is, there are a lot of them involved over a 30-year period. Imagine that, continuous funding for over a 30-year period. In Chile and in Hawaii, that's where the telescopes were. And so they're unraveling the mystery of what creates black holes and the impact of those black holes. What's very clear from their work is that black holes play a huge role in shaping the universe, because the trajectory of stars anywhere near those giant black holes is changed. That's the intro to next week when we talk about general relativity. So that's going to be a really interesting session. So we're going to talk about general relativity, and we're going to talk about black holes. So I think Stephen Hawking as well next week. So that's what's coming. You won't be watching me work on the blackboard here, or whiteboard. So thank you very much. But think about those things and go to the website. You might want to look up some of those reading materials. Oh, one last thing I'll mention. If you want to find out about what's happened with those Nobel Prizes, go to nobel.org. It's that simple. And they have PDFs. And one PDF is for, I would think, scientists, kind of a summary for people in the know. But the other one is for people like us. And they're well written. And so if you actually want to know what's going on and it's very well communicated, it's a good way to do it. And it would be, go to the one on the stuff on the black hole stuff for next week. That would help a lot. Okay, well, again, thanks very, very much.